Here's another projectile motion problem that's very similar to the first one in the compound projectile motion problem number 1. In this one, we have a ship that is approaching a dock at 45 centimeters per second. I'll actually label that here. An important thing, whenever they give you things like centimeters per second, I would always recommend converting this stuff to meters per second. And remember, there's 100 centimeters in a meter, so 0.45 meter per second. Okay, so what we want to do is we want to take a piece of landing equipment and throw it from the top of this tower and hit the ship before it can dock. The equipment is thrown at 15 meters per second at 60 degrees above the horizontal. So if we kind of do something like this, we have 15.0 meters per second. That's the kind of initial velocity that we're throwing this at. From the top of the tower, at the edge of the water, 8.75 meters above the ship's deck. So this basically tells us that the initial position in the y direction that we're throwing this at is 8.75, and when it comes down and hits the ship, we'll say it's kind of like located right here. This is at, say, y is equal to 0. So forgive the poor drawing, but this is the idea that the problem is getting at. And so for the equipment to land at the front of the ship, like I've drawn here, at what distance d from the dock should the ship be when the equipment is thrown? And we don't care about any complexities like air resistance. So in our picture, what is d? Well, that's this distance right here. We can kind of think of this as the sum of two distances, really. It is the sum of what we'll call distance 1, d1, which is the horizontal distance covered by the equipment as it's thrown off the tower and lands on the ship. And then there's a second distance, which we'll call perhaps a d2, which is the distance that is covered by the boat as it's just sitting in the water while it's waiting for the equipment to land on it. So what's the relationship here between these? Well, capital D, the thing that we're trying to solve for, is the sum of d1 plus d2. That is how far away we want the ship to be when we throw the landing equipment out, so we can just hit the front of the ship in time. So let's solve for d1. In order to do that, we are going to need time. And we can solve for time using the following equation. I'll kind of put a box around this a little bit to separate it. We can say that the final position in the y direction is equal to the initial position in the y direction plus the initial y component of the velocity times the amount of time plus 1/2 at squared. What's the final position in the y direction? Well, we said that is once it hits the ship at y is equal to 0. So this is 0. What's the initial position in the y direction? Well, that's this 8.75 meters at the top of the tower. So we can rewrite this as 8.75 meters. what is the y component of the initial velocity? Well, that is 15.0 sine of what angle? Well, we were told this was 60.0 degrees, so sine of 60.0 degrees. That's being multiplied by a time, plus 1/2. What's the acceleration experienced in the y direction? Well, that's gravity, negative 9.8 meters per second squared, times t squared. So let's perhaps rewrite this because it's getting a little messy. I'll leave the units out for the time being since I'm running out of space. So 8.75 plus 15.0 sine of 60 degrees and minus 9.8 divided by 2 is 4.9 t squared. So, oh, I forgot a t. There we go. If we take a look at this expression, it's very similar to the situation we had in the first problem where we run into a quadratic expression. And let me label A, B, and C like I did before. Remember, A is attached to the highest exponent variable. So right here, A is minus 4.9. We said B is equal to this quantity here, 15 sine 60, and C is the leftover component here that doesn't have a variable attached to it. That's C. And what do we do with ABC? Remember, we use the quadratic formula to solve for the amount of time it takes for the landing equipment to hit the ship. And how does that go? Well, the time is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. And I will leave it up to you to plug all this information in and get the 2 times. One will be negative, which is non-physical, and we will throw away, and we don't care about. The other time that we get is 3.207 seconds, around there, and we will be keeping this time. Now, in order to solve for what d1 is equal to what? That's equal to the x component of the initial velocity times the time that we just solved for. 3.207 seconds. And if we plug this in, we get 15.0, the x component, so cosine 60 degrees times 3.207 seconds, which is what we just solved for. And this is equal to what? I get 24.0525 meters. Okay, and you will likely get something very similar to that too. So that's just D1. That's not capital D. We need to figure out what D2 is. And what is D2? That is the distance that the ship moved just from being in the water, because the water is imparting this velocity of 45 centimeters per second, or 0.45 meters per second. And that's a very simple calculation to do. We know what the rate is. That's the 0.45 meters per second. And this movement, this rate, like due to the water, is occurring the entire time we're waiting for the landing gear to fall onto the ship. And that takes the 3.207 seconds. So let's multiply it times 3.207 seconds. And I get 1.4445 meters. And so we have D1, we have D2. We said that capital D, which is what we want to solve for, is the sum of these two numbers. So let me write this in red. D is equal to 24.0525 plus 1.4445. And what we want to do is truncate that answer to the smallest number of significant figures in the problem description. So here I see 3, here I see 3, here I see 3, and here I see 3. So when we take the sum of these two numbers, D1 and D2, and we truncate them to 3 significant figures, we get 25.5 meters. And that is the answer to the problem. This says that the ship needs to be 25.5 meters out from the dock in order for us to throw the landing equipment out with these particular values and just hit the front of it before it moves any closer. And that's it. Thanks for watching.